In this video, we're going to discuss definite and indefinite integrals of vector functions. So we're going to start by defining them, and then we'll look at a couple examples. So if we're given a vector function, r of t with components f, g, and h as usual, we'll start by defining the indefinite integral. So that's going to be the set of all vector functions so the set of all functions whose derivatives is r of t. Right? So in other words, if capital R of x or capital R of t is an antiderivative of lowercase r of t, then the indefinite integral of r dt is equal to capital R of t plus c, right, where c is an arbitrary constant vector. So this looks exactly like it did in Calculus 1 when you introduced the idea of an integral of a function, of an indefinite integral of a function particularly. The goal is to find one antiderivative, which is just a vector whose derivative is the given vector. And then the indefinite integral is that antiderivative plus all arbitrary constants. All right, and the justification for that is exactly the same as it is in Calculus 1, so we're going to overlook that here. But again, the plus c will be an important part of this indefinite integral. So for a quick example of this, let's say I have a function r of t, which is given as 2 cosine t I plus 3 sine t j plus t k. Okay. And I want to compute the indefinite integral of this function, so I want all of the antiderivatives of this vector. And so to do this, all we need to do is find an antiderivative of each of these components, because remember, the derivative of a vector is the derivative of each component. And so we just have to antidifferentiate each component. So an antiderivative of 2 cosine t is going to be 2 sine of t. An antiderivative of 3 sine t will be negative 3 cosine t. And an antiderivative of t is going to be t squared over 2, or 1/2 t. Right? And then we also want to include the plus c at the end, an arbitrary constant vector added on, which would allow for any constant to be added to any of the three component functions. Right? So instead of 2 sine of t, we could have written 2 sine of t plus 5 times I, minus 3 cosine t plus 2 pi times j, and plus t squared over 2 minus the natural log of 74 all times k. Right? So we could have included a constant in any of those terms, but what we typically do is group all the constants together as a single vector at the end. So to define a definite integral, so we want the integral from a to b of a function r of t. is defined by the following rule. And that is we're going to define the integral from a to b of r of t to be a vector, and each component of the vector is going to be the same integral over the component function. So the first component is going to be our integral over f of t from a to b. The second component will be the integral from a to b of g. And the third component will be the integral a to b of h. And so we can then break this down, an integral of this vector, as an integral of component functions and use integrals from Calculus 1 to be able to compute this. All right, so this means that we can then use the fundamental theorem of calculus on these three component integrals. And so really just once we understand that how to define the integral of a vector function, that it's the vector of the integrals of the components, we now know how to do this. Right? So let's say, for example, we use the same function that I just had in that previous example. What was it? It was r of t equaled 2 cosine t. I'm going to go ahead and put this in component form. I know it was in standard basis form before. 3 sine of t and t. And so I want to compute the integral, let's say from 0 to pi over 2, since we have trig functions here of this function. Right? And so what we want to do is take the integral from 0 to pi over 2 of 2 cosine t, the integral from 0 to pi over 2 of 3 sine t, and the integral from 0 to pi over 2 of t. And we just want to compute each of these three integrals. So this will be the vector 2 sine of t evaluated from pi over 2 to 0, negative 3 cosine of t evaluated from pi over 2 to 0, and t squared over 2 evaluated from pi over 2 to 0. Right, we already found those antiderivatives. So now we have sine of pi over 2 is 1. So this is going to be 2 times 1. Sine of 0 is 0, so I get 2 minus 0 there. For the second component, I get negative 3 times the cosine of pi over 2, but cosine of pi over 2 is 0. And so we're going to subtract negative 3 times cosine of 0, so that would be negative 3. So we're going to have 0 minus negative 3. And the last one, we're going to have t squared over 2 evaluated at pi over 2. So that's going to be pi squared over 8. And then subtract 0 is 0. So we get the vector 2, 3, pi squared over 8 as our definite integral of this particular function r. Now, one of the most basic uses of an integral is to go from acceleration to velocity to position. And so we can also do these kind of initial value problems with vectors as well as just as you could in Calc 1 or Calc 2. So for an example, let's suppose that an object is shot by a slingshot with an initial velocity which we'll call v of 0, 0, 10, 64. And this will be in feet per second. Okay. So notice this means that this initial velocity, it's telling us not only the speed, which we could compute with the magnitude of this vector, but it's also telling us which three-dimensional direction we're shooting the object in. 0 along the x-axis, 10 along the y-axis, and 64 along the z-axis. So we're shooting this pretty far up in the air. So what we want to do with this information is we want to find the position, the position vector, r of t, for the object. And this is at all times t, not just at a particular time. And so what we need in order to do this is we need a couple other pieces of information. So we're going to assume the object starts at the point so we'll call r of 0, 0, 0, 4. And that the acceleration due to gravity is a of t equals 0, 0, negative 32 feet per second squared. Okay. Now these two assumptions here, if we think about it, they do make sense. The initial position at 0, 0, 4 means that it's being shot from 4 feet off the ground. So, a normal-sized person, if they were shooting a slingshot, it would be about 4 feet off the ground to start. And this acceleration due to gravity, it makes sense that this is a constant vector, since this is, gravity is a constant force. Right? And so we're going to use this information to find the position vector r of t for this object at any time t. So our starting point is to observe that the velocity vector v of t is going to be the indefinite integral of a of t. Okay. And so this is the indefinite integral of the vector 0, 0, negative 32, right, which is a constant vector. And so to compute the indefinite integral of a vector function like this, we just compute the indefinite integral of each of the components. And so we're going to get the vector 0, 0, negative 32t plus some constant vector c. Right? And this constant vector c becomes important because we need to figure out what the value of that constant vector c is actually, what it actually is, in order to find the specific velocity vector v of t in this case. Right? And so in order to do this, we're going to use the fact that v of 0 is equal to what we were told, which was 0, 10, 64. Okay. Right, so v of 0, v of 0 in this case is what we get by evaluating this vector at 0. Right? So we get 0, 0, and I'm going to write negative 32 times 0 in here, but of course that's equal to 0. Right, so we need v of 0 equal to this, and from this we can conclude that this constant vector c must equal 0, 10, 64. Okay. Now I'll point out that this is not always the case. It's not always that the initial velocity will be this, this particular vector. It it was the case in this particular instance because our acceleration vector was constant, right? So now what we can do is go back to our velocity vector. And so our velocity vector is going to be 0, 0, negative 32t plus this constant vector c, 0, 10, 64. And so when we add these vectors, we get 0, 10, and negative 32t plus 64. Right? So now we have this velocity vector, and it's a very particular velocity vector. It's not the arbitrary one with a plus c. It's the one that corresponds to with our initial velocity that we were given. And now once we have the velocity vector, we can just repeat this process to find the position vector. Right? So we just saw that the velocity vector is the vector 0, 10, and negative 32t plus 64. And so we want to find the position vector r of t. And that we know is the integral of the velocity vector. Right? And so in order to find this, we find an antiderivative of each of the components of this vector v. So 0, 10t, and then here we will get negative 16t squared plus 64t, and then we will add on a constant vector at the end. Right? So that will account for the plus c that should be in each of these components. We'll just gather all of those at the end. Right? And now this is where our initial position comes into play. Right? So we were told our initial position r of 0 was 0, 0, 4. And so r of 0, which we can see here, r of 0 will be, from our function, the function 0, 10 times 0 is 0, and negative 16 times 0 squared plus 64 times 0 will be 0. And so r of 0 here is just r of 0 plus c. And so from this, we conclude that c is the vector 0, 0, 4. Right? And so our position vector r of t is given by components 0, 10t, negative 16t squared plus 64t. And then we have to add on this vector c, 0, 0, 4. And so it doesn't change anything in the first two coordinates. It just adds on a 4 into the third component. And so our position vector for our object that was shot from our slingshot is given by this vector function here. And so if we actually wanted to answer any questions about this particular object, various algebraic kind of questions, we could use this vector function to answer those.